My name is Carsten. I'm the electronics guy from the part-time scientist. I'm also a full-time scientist at TU Hamburg. And I worked on a little project that's called PSHDL that I want to present today to you. And first of all, a very short overview of what you can do with FPGAs. So FPGAs are very awesome. They are logic that you can configure. And the strength is, for example, that you can do many things in parallel and that you can do by high bandwidth things. And also, if you're known from interrupts, they take a long time until they're happening. And in an FPGA, you don't have that delay. So what is a good use case for an FPGA is, for example, that you want to toggle some bits in a high-frequency trading application and see what happens. Or you want to put an overlay video onto the HDMI video signal. And there are many other cool projects that you can do with an FPGA. So yeah, this is why I want to get people into working with those. And also I've heard that in front there is a Datenkrake guy, and you can buy an awesome board from them. And then you can do your hacking on FPGAs, and there's a CPU on it as well. So in a regular CPU, you have tasks that are executed in parallel, in sequence. And on an FPGA, you basically dedicate a block to a certain function. And so this function can then happen at the same time as the function A can happen at the same time as function B and function C, for example. So this is pretty cool. But programming them is a pain. There are many programming languages called HDLs, which is hardware description language. VHDL, Verilog are very popular. MyHDL, JHDL are not so popular. And then there are some that try to emulate the C behavior, and some of them are using a dedicated template like systemc. And there are also all kind of other high language synthesis tools, as they're called, that are trying to compile C code to RTL logic so that you can configure the FPGA with it. But they suck. So a short overview, VHDL is very old. It's developed in 1987. It's based on our most favorite language, ADA. Who likes ADA? Who knows ADA? Oh, okay, no one, I expected it. And when they first invented it, it was to actually put some documentation about what is happening on the ASIC. And then they thought, now we have all the documentation. Why couldn't we use it for simulation? And then they started, when we can use it for simulation, why won't we use it for programming as well? And so they started with a perfect documentation language and later started to abuse it for synthesis. And yeah, so VHDL stands for, the HDL stands for hardware description language, and the V stands for very high speed integrated circuit. Yeah. So I think even the name sucks. And how much it sucks, it's like if you're programming in VHDL and FPGA, it's like a spaceship, and it doesn't have to be rocket science. Or if it has to be rocket science, it can be as awesome looking as our rover at least. So. As most of you have probably never programmed in VHDL, I first have to give you a demo of how painful it actually is. And I will just do that now. So after you downloaded the 20 gigabyte download from, let's say, Xilinx, you will find those really, and it takes like half an hour up to 6 hours to install. I once, at the last conference, at the last congress, I did a seminar, and the seminar was 6 hours, and one person started to install it, and when the workshop was done, he wasn't finished yet. So it's really that bad. And it looks even worse if you don't have any screen space. Can you hide the... I hate Windows. Anyway, okay, so let's create a new project. By the way, this is PlanAhead. PlanAhead is a newest tool from Xilinx. It's It's supposed to be the nicest UI you could imagine. It's awful. So you say, okay, let's create an RTL project, and I want to, oh wait, no, that was wrong. I want to create a new file, and I want to create it in HDL, and I want to create a counter like this. And then you go target language VHDL, then you go like next, and whatever that is. And then you choose a part, whatever. And then you click finish. It creates your project. And okay, we need a clock for a counter. That should be this one here. And we need a reset. And because we want to toggle the LED, blinking LED is always the default one that you do. So let's make this. And then there is something happening. Okay, this looks really much worse than with a high resolution screen. Yeah, so there's just not. I assume you can all read it, right? Let me see if oh, that's much better. So in VHDL you have, declare a library that you're using standard logic, stuff like this, and then you have a clock, reset, and LED. And as you may know, if you are programming, then you need to start with a process, and you need to say that it depends on the clock and the reset. And then you have all those Pascal style begin, and you have to say end. And if I'm not mistaken, you have to say end process here. There must be a semicolon. I haven't programmed VHDL in a long time, so if reset is, let's say 1, then that's good. That gets boring. So you're writing all this code, and let me quickly cheat a little bit. And I will just copy the source code. Whoops, no, wrong one. So I assume I was typing all this stuff. And you can see it's a very verbose language. You have all this kind of stupid stuff here. If you have to describe a register. So if you want to store some data in an FPGA, you have to describe a register so that it can hold the value until the next edge. And it's always at the rising edge, it's kind of latching the data that is currently there. And so if you want to get a register, you have to describe it in a way that you want to have it in VHDL. And then, oh, I forgot the library stuff. Let's copy that as well. Oh, and there's a really cool feature of VHDL is that you have to put a semicolon here, and not there, and then you have to declare a part here, but there is no begin because they're using braces there, and yeah, all kind of funky stuff. So, and wow, this is. Well, let's say we want to simulate it. So, oh yeah, be safe. Let's hope I did everything right. Simulation top module with counter. Did I really? No, it's forced. Yeah, like this. So this is all kind of safe explanatory, right? You know what you have to do. It's all easy stuff. And then it's elaborating. Okay, don't need this, this, or this, and this. No, okay. So I, whoa. No, Okay. So then you have to, in the simulation, you have to do some stimulation of the unit that you are testing, and I'm just doing that with a little script, and the script is also measuring the time that it takes to run the simulation. So what I basically did is I created a counter that is counting 20 bits up, and I'm using the most significant bit to toggle the LED. And if you have 20 bits, you're dividing the clock by 2 to the power of 20, so this is quite a bit. And yeah, oh cool, there. And you can see here, this is the clock. It's really fast, and the LED is blinking really slow. And remember this time, it took 16 seconds to toggle the LED 5 times. I will ask you later how much that was, and if you're right, you will get a free sticker from our Hell Yeah, it's rocket science stuff. By the way, here, this is the slogan of our team, the part-time scientists. So this is the fast clock, and it's running at 1 nanosecond. Okay, so that who found that very intuitive? What I just did? Oh no, you're kidding. Okay, so I thought this is ridiculous. You know. Oh, there's a question. Yeah, Verilog is a little bit better, but the problem is you're still describing. You still have to describe what you're doing, and you're not saying what you want. Well, okay, it's shorter, yes, but I don't like it that much. But yeah, mostly it's because I'm too tired to learn. Yeah. Yeah, I will probably sometime learn Verilog. Verilog is the other language, and it's a bit shorter there, he's right. But it's not much more readable, and the workflow is quite the same. So I invented PSHDL, which has a really cool acronym. It's a plain and simple hardware description language. I'm so proud. You know, I found this, and then I created this logo. This was the second thing I did. And the idea is that I create a language that has a very modern syntax, so that people that are coming from the C side, not the C side, but program C, they should be able to see what is happening there, even though they have no idea what this hardware description language does. And programming in a hardware description language is a bit, as one participant of my last workshop said, it's like programming brain fuck, because you have to think in a different way. I cannot help with the thinking part, but I can make the syntax nice, and I can try to ease the learning curve a little bit and provide a very good tooling so that people are getting error messages that are very helpful. I'm working on that. But it should also be very powerful. So one of the things that are happening in VHDL a lot is that you have to create a lot of boilerplate code that is really boring to write, but yeah, it has to be done. And so in PSHDL, I included a code generator that is automatically generating code for you, and has all kind of other features. The idea of PSHDL is to mainly design for FPGAs and create synchronous designs there. So those are the ones that are with a single clock. But it doesn't mean you have to have just one clock. You can have multiple clock domains if you want to. It's possible, but the primary use is with one clock domain and it's synchronous. So just a little bit code, a few code examples here. The first thing every student learns is the wrong way to do a bit adder. It's by using XOR, A, B, and C in XOR is the sum, and the carry out is A and B, XOR, Cn, and A and B. And I hope that who could understand that, you know, just by looking at it, the bit adder. Oh, okay. Okay, I'm just saying, there's no one seeing how many hands are raised. I'm saying everyone raised their hands. But the next thing is a bit more clear. You know, if you create a counter, you need a register, and if you want to have a register in PSHDL, you just say register. You know, the counter is a register, and on every clock on rising edge that it gets, it increments by 1. That is actually quite intuitive, I guess. And there are those curly braces which are for accessing a single bit. You can also access range, and you can declare how wide signals are and stuff like this. And if you want to go fancy and you want to have your register in a very different taste, like have it on the falling edge, you can configure that if you want to. This is a more complicated example, but I really promise you that the VHDL code for that is at least 3 times the size, because it's so verbose, because you have to declare enums, and you also, the instantiation is not as easy as, for example, what I'm doing here is I'm instantiating a master driver for the I2C bus. And I'm just accessing all the ports with I2C.clock, for example, is the clock in port of the I2C master byte controller, which, by the way, is just a plain VHDL module, so you can just import VHDL code very easily, of course, because that's, most of you probably don't have PSHDL code yet. I'm really hoping that this is going to change, but so far I have to live with that. It has ternary operators, which is, everyone is wondering what's special about those. It's not in VHDL. And yeah, you can describe you don't have a process where you have to describe everything. But as you don't know VHDL, this doesn't make much of sense to you. But I'm going to show you a little bit something. I also worked on some tooling so that you can get started pretty quickly. So the idea that I had with PSHDL is that the vendor tools, the 20 gigabyte Xilinx Ether tools, I want that you have to use them very late, so that you don't get confused by all those knobs and stuff that you have to do there, but that you can quickly start and get your blinking LED in like no time. And yeah, I will demonstrate you how to do that. And there is a website where you can go to, and you can enter your PSHDL code, and you get your VHDL code, and then you can use the VHDL code for that. I also worked on a new website, on a new UI that I'm going to present to you later, or no, that I'm going to present to you now. Yes, I do that. And this is written in Dart. And what you can see here is there you have a little reference where you can, this is a tutorial, where you can get some introduction on how PSHDL works. And there you have a code tab, and all the files are stored on the server side, so you can create a workspace. Let's say, of course, you're all entering your valid IDs, your valid email addresses here. Let's add an S there and there. Let's do this. So, and you can create a new file, and then you have, you have syntax highlighting, and this is, let's put it this way: if you're paying like $3,000 a year for the Xilinx tools, at least you know that they are not wasting it on designing a good UI, So one of the tools that I was using was very expensive, and it had a syntax highlighting on save, and it had a single step undo. This is the state of how the tools are at right now in the EDA field. Of course, there's an Eclipse plugin from Zigazi, which is really nice. It has syntax highlighting and stuff like this, but the problem is the error messages are not there, because the problem is that let's save this. The problem is that the VHDL can be used for so many things, for example, simulation, but also for programming FPGAs. And so they don't know if they should display, the message that the stuff that you just described is not a valid register, because actually in a simulation this might be correct. And so making correct error messages in an editor is very hard for Verilog or VHDL. And yeah, so even my web stuff here has, it shows some error messages if you're doing this. But what I really want to show you is some of the examples. So yeah, this is how you describe a replicatory idea. You just can have arrays of instances, and but this is actually a bit more exciting. So most of the time when I am developing something in VHDL for an FPGA, I also have a processor. In our rover, that's a power PC, and there's a bus called the PLB bus, and attached to that is then my logic that I am developing. And so from the power PC, I can add, I can write to the memory, and that goes to the IP core, and this is pretty cool. But there is a lot of boilerplate code that you have to generate for that. Oops, no. Let's see what happens if I. There we go. So, and yeah, let's compile the stuff. And what you're seeing here, this is the code that is generated, the VHDL code that is generated for this little example. And most of the code that you're seeing here is for decoding the bus. And the little, where is it? There it is. This is what you actually wanted to do. You wanted to add A plus B and put it in a different register. And this is all the boilerplate code that you have to generate. But you don't just have to generate boilerplate code, but you also have to create other fancy files like, I think this is a MOA or POA. Oh, this is a POA. And you have to also implement the MPD file, and then you have to have a wrapper around the PLB logic stuff, and like this. And so this is a lot of code that has to be generated for just doing something very simple. If you look at the PSHDL code, this is really simple. So this is, by the way, this is one of the features of PSHDL that you can include another domain-specific language. So here in a generate statement, you can define. You have to do that in Java, but you can define a generator, and this generator can then generate all the code from you from what it sees within here. So this is a domain-specific language for describing memory layout that you can access with bus.a. You can access the register A, and you have 4 of those, so you can go from 0 to 3 and add those. Nope, there we go. But I'm not stopping here, but I'm also doing something more interesting. For example, sometimes you're wondering where in the memory actually is the stuff that I just described, and it's generating you a memory map where you can see where all the data is. So, for example, if you're writing at offset 0, then the upper 16-bit will be A0, and the lower 16-bit will be B0. And at address 4, you will find the result. And there is also some code for that you can copy-paste for accessing from a base address and stuff like this. But I'm also generating some C code for you. So there is, where is bus access H? There. So you have those nice set functions where you can just set A and set B and fetch your result. And those functions, have their. So this is what you're basically doing here. You can also define warning so that when you're accessing, when you're writing a 32-bit value to a 16-bit value, you can get a warning or something, or do something else, crash the system or whatever. And so this is all generated for you automatically from this very short description. And so this is the power of the generators that you have in PSHDL. There is also nothing happening here, and I'm coming to the simulate button soon. So this is PSHDL, what you can use for describing logic in an FPGA. But I wanted to go a bit further. I wanted to create a simulator as well. For Verilog, there is this very awesome Verilator that you can use for converting Verilog into C code, and then you can simulate the C code. And if you're, for example, developing your next H.264 codec, you can feed the data from the C code directly into the simulation code and get result back and verify that your Verilog code is working as expected. And this is a very powerful feature. And in PSHDL, I basically did the same. I created what's called a PSX, a PS executable. And this is a very simple bytecode. It has like 26 instructions. And yeah, then you can develop your own interpreter for it, or you can convert it into other code. And so far, you can convert it into C code, Java code, and Dart code. Does anyone know what Dart is, by the way? Okay. Dart, by the way, is a new language from Google for web developing, because I hate JavaScript. I didn't really want to not learn JavaScript for doing this stuff, so I use Dart. And Dart has an own VM, and that's pretty fast. So I want to give you a rough overview of how fast the simulation in PSHDL actually is. And the purple bar is GHDL, which is an open source VHDL simulator, and it's painfully slow. If you look at the time scale, it's logarithmic. So it's twice as slow as the iSim. iSim is what you get with Xilinx tools. It's okay, but if you see the yellow bar, that is actually the fastest commercial simulator that I am aware of. It's QuestaSim. But if you look at the blue bars, that is PSHDL. So PSHDL is in the interpreted mode, which is the light blue one, about the same speed as a yellow bar, as QuestaSim. But if you are generating Java code or C code, it gets really, really, really fast. So, for example, for the Ripple carry idea, it takes about 1.5 milliseconds, while iSim takes about 1.5 seconds. So that's 3 orders of magnitude difference that you get. So you can simulate, what I want to say is that you can simulate PSHDL very easily, and it's pretty fast. And I want to give you a short demo, because I also have the counter here. This is a 20-bit counter that I was just running in the simulator and iSim. And as you may remember, it took about, what was it, 16 seconds to simulate. And let's see if I can beat that. So I do the same, and I actually forgot which number I wanted to look at. I think 5 is like 1, 2, 3, 4, 5. So that is 17.7, so that's 1.5 seconds. It's running in the browser. The simulation of PSHDL in the browser is 10 times faster than iSim that you're getting for free. And another feature, you can also have a blinking LED visualization. So this is my vision. I want you to be able to go to the Learn page, take an example, put it into code, put it into simulation, and get your blinking LED in less than 5 minutes. And this is really what I'm aiming for, is that to create something that is easy to learn, so that people are not afraid of learning how to program FPGAs, but they might actually enjoy it. That would be pretty awesome. I also want to bring some of the tools that we are known from the software development, like JUnit tests, you know, to PSHDL. And yeah, I'm working on that, and so far I'm what you can see is there. It's working quite okay. If you're using it, you will encounter a few bugs, and I would be very pleased if you file me those. So in the future, I want to have Verilog output for the one person that wants to have Verilog, and I want to add some configuration so that you can not just start with coding, but you can also upload it to your FPGA. And I want in the very far future, I want to have interactive tutorials and a website that is dedicated for learning how to program FPGAs. So, yeah, my vision is that people should be able to learn code, analyze, simulate, and synthesize all their code with just a few clicks. And I can provide you with the infrastructure for the left side, but I need you to help me with that, to teach, to share, to collaborate, and to improve what you can do with that. And with Run Everywhere, I'm really curious because you can generate C code out of the PSHDL code. I really would be curious to see where you can run PSHDL code. Getting a blinking LED in a few minutes is not a new idea. If you everyone probably knows Arduino, and it changed the way that people were able to program embedded device ATMLs. Every one of us probably was able to program an ATML before, because we know that there are registers and there are stuff, and we need to put a value there, and then we need to bit mask there and do this. But not everyone wants to learn all this stuff. You know, some people just want to have a really nice UI with a few buttons, and they want to have a one-click solution where you can toggle in an LED very quickly. You know, toggling LED is awesome. So, okay, maybe we can do something more exciting. By the way, the rover that you saw in the picture, that's programmed in PSHDL most of the time. So my vision here is I want to create the Arduino for FPGAs, and I need your help to accomplish that. I hope you have seen what I have put on the floor so far. It's GPL code, so you can download it, you can work with it. You can download it and you can build a command line compiler, but I would kindly ask you not to use it. There is a REST API that you can use, and the advantage is that I'm updating the compiler on the REST API more frequently, and also I can learn from your mistakes that you're doing and the bugs that are encountering on in the compiler that are definitely there. Anyway, I want to say thanks to the students that helped me for improving this the PSHDL everything, Henry, Andre, and Henning. And if you want to buy awesome, hell yeah, it's rocket science t-shirts, you can go to shop.ptscientists.com. So that was basically everything from my side. And if you want to follow me in a non-creepy way, you can do that with this social media outlets that you find there. Choose the one that to your most liking. And yeah, thanks. Any questions?
There is a tab for synthesis and you set it up, and that seems to be kind of the pointer that you actually generate code for the FPGA. Right now you still need the software.
Yeah, no, wait, yeah, okay, so the question is, what does a synthesis tab do on the compiler? So far I have to say, this is the place where you can see the generated code. You can also download the code, of course, but then you have to put it into the tools, into the tool chain from Xilinx. There is a Webpack edition that basically every vendor has a free version that is limited to small devices that you can use for programming. And but there's something that's not in there yet because I wasn't able to do that. There is a streaming API happening in the background. So what I really wanted to do is that you have a local client that where you just enter your workspace ID and then you then it's attaching to the event stream, and when the compilation is happening, then it fetches the results, goes through the simulation, and puts the results up there for you to show, so that you don't have to do it on your own. Yes? Yes. I was thinking about that. The thing is, I have a license that is much more capable than Webpack license, and it would be very interesting to figure out how long it takes until they notice that there is a license available online that everyone can use, but they don't have any benefits from it. But I'm definitely interested in talking to them to see if I can do the server-side compilation. Yes, this is something that I really want to do, so that the synthesis tab is really where you can download the bit file and then get it on the FPGA up and running. Any more questions?
I guess another question in that case from back here. Actually, I have three of them, so
Okay.
so the first question actually, in terms of the ADI, which is great in itself, is from my experiences both with Atmos as in VR Studio or as CVR versus Arduino platform, is that once you get stuck in the Arduino platform by taking advantage of this easy learning curve, going to actually be able to do something difficult is possible, but you are working slightly with things like how do you actually make sure that linkers link it correctly, and how do you actually check your optimized assembly with all of that. How do you plan on addressing this issue with PSHDL? Because it's more difficult in HDL.
Yeah, so the question is how can we enable powerful features with a simple language like PSHDLs? And the answer to that is threefold. The one thing is you're always getting VHDL code, which is the code that you can then put into the powerful tools, and you can, if you want to, actually use this use the power of VHDL then and modify the VHDL code. It's very readable. It's, if it wouldn't have disappeared, I would have showed you. It's really there is nothing fancy going on. The code is quite clear to read. It's not gibberish, and so you can modify. You can generate the VHDL code, put it in there, or you can create a module that you can then instantiate in PSHDL, where you're doing fancy features that are just allowed in VHDL, or you can generate native functions. Native functions work by in PSHDL. I have to say that PSHDL is not just a compiler; it's a framework. There are many extension points where you can hook into the code generation. You can have an output generator. You can have you can add native function. Native functions basically get called like here. There's a function call at this statement. What code, VHDL code, should I generate for it? And so you can hook into this, and yeah. So those are the three possibilities how you can extend PSHDL code. You said three questions, or was that one? Ah, okay.
question here is, how do we go with that level of flexibility built into everything in a sustainable way?
Yeah. Okay, so the question is, how can you modify generators so that they are generating the most powerful code that you want to have? And well, the basic way it works in PSHDL with code generators is that you have a domain-specific language for configuring them. You don't have a UI, and the domain-specific language then has to accommodate for the use cases that you want to have. For example, one of the cases that you could do is that in the domain-specific language for generating memory ports, you could include another language for modifying something in a certain way. But I think that I really want to think of PSHDL as a starting platform. You can really do powerful things, but once you're so constrained by density or by speed or whatever that it sometimes doesn't make sense to use it anymore, but to go down to VHDL. I'm not aiming for PSHDL to be the ultimate replacement for VHDL or Verilog, but I want to have something that people can start with, and yeah, so that's basically the answer to that. Yeah.
Okay, so I guess I'll go with my last question, kind of building it up towards it. I think the real test for PSHDL, and actually it also goes back to why people are using FPGAs, why people are drawn to FPGAs from every other Arduinos, ARM processors, anything that is simpler to work with, is the super capable FPGAs have. So I think the real test of PSHDL would not be blinking LEDs. Implementing something, and I'm going to point out what are going to be key parts there, like PCI Express serializer, deserializer as processors, which on one hand, device-specific hardware, because this is suddenly a thing that actually has to be device-specific. On top of it, 66-64 decoding, which is the algorithmic thing, but needs to be very fine optimized. And finally, actually being able to talk to it on the other end.
Yeah.
And my question here is, how do we actually address these very specific issues so people who go to PSHDL can actually see that kind of example and get started with big FPGA things?
Yeah, so the question is, how can you instantiate the features that are device-specific in a language that is not capable of instantiating them directly? And there are two ways. The one way is, for example, a DSP slice can be described in such a way that that is behavioral oriented. So the Xilinx tools are analyzing the code and see, oh, I could do this multiplication and this addition actually with a DSP slice. So this automatically infers a DSP slice from the source code, and I think that is the best way to deal with those device-specific things, because once you get hooked into the system of instantiating a DSP48E slice by hand, you cannot change the vendor. You cannot change the platform, and so this is basically the same as with any library that you have on the CPU side. Once you're getting hooked into using the Intel-optimized mass libraries, you cannot go back to use a more general-purpose one without a big headache. So the best way is to describe it in a behavioral way, and if you can't do that, then you can still do the same thing as Xilinx does. Xilinx is not giving you the source code of the block anyway, but you're just instantiating a black box, and you can do the same in PSHDL, as I was showing earlier. For example, the I2C thing that I was showing off, that was actually VHDL code. There we go. So as you can see, you're just importing VHDL work dot, and then you can instantiate whatever you're expecting to have in your tree there. Yeah. So that is so if you actually I'm also working on the primitives to generate the PSHDL interface that you need to instantiate all the primitives for Xilinx. I have an automated converter that is reading those components and then generating the interface for you so that you can use it and instantiate it. Yeah, and I'm hoping that I will be able to do that for the other vendors as well and provide that so that you can use it easily. No more questions, really? If you have another question, I will give you a sticker, a really awesome sticker. Where are they? I know I took them. Anyway, if you want to have a sticker, just come here and we can have a talk. Also, I brought 10 Xilinx FPGA boards with me, so if there is some hackerspace where you can sit down, maybe someone wants to put PSHDL to the test and do some more blinking like on a real FPGA board. So, thanks. Huh?
Have you considered, where have you talked to the people doing the Papillon? There's something, we're trying to make an FPGA like Arduino.
Who are they called?
Use Papillon, like direct light.
Oh, okay. No.
Because that seems like it's operation. I don't think they have a good solution for the actual code. They basically assume they can have 2 or 3 different bit streams on the device.
Okay. Yeah, that's not really helpful in saying okay in the camera. Yeah, so there's an open source FPGA, and I guess I will have to contact them. I didn't know them yet. One more question? No. Okay. Thanks then. And yeah.